This is an example of the first order transients game in Circuit Tutor on level 2, problem type 1, which is going to be an RL circuit. So I'll go into the first order transients game. I'm assuming that we've already watched the introductory tutorial or already done that. So we'll skip that for right now, and we'll select a medium level problem. Okay, so this problem, of course, as always, involves a switched circuit, which is going to create a transient once that switch closes at t equal to 0. And in these types of problems, I always need to analyze the circuit at 4 different times, namely at 0 minus, which is right before the switch is closed, when I can assume I'm in steady state since it's been open for a long time. At 0 plus, once the transient has been initiated, then I'm not in steady state, and I may need to analyze it there. At t equals to infinity, which once again I will be in steady state after the switch has been closed for a long time. And then I also need to find the Thevenin equivalent resistance seen from the terminals of the inductor for t greater than 0, because that's going to determine the time constant that sort of gives us the characteristic behavior of the circuit as a function of time. So again, we can always give up if we get stuck, and there's some help available there, but let's begin by analyzing at 0 minus. We always want to do this in chronological order. It isn't possible to go backwards. Okay, so it's basically labeled it now with the SOT variable at 0 minus here, which is what we're trying to find. And it tells us the instructions, which start by reconfiguring the circuit to change the switch and the reactive element as necessary. And then we have to come into the circuit editor, if necessary, to simplify it and then solve the circuit. So let's begin by clicking reconfigure circuit here. And remember, we're not allowed to simplify the circuit in this mode, only to change the switches and the reactive element. So here, because it's 0 minus right before the switch is closing, that switch is going to be an open circuit. So I will simply delete that by pressing the delete key here. So that's gone. And now the inductor, remember, we're going to be in steady state. So as V equals L di dt, that inductor is going to have to, since di dt is going to be 0 in steady state, since this switch has been, we're presuming, in this position for a long time, the voltage will be 0, which means it's a short circuit. However, before I change that into a short, I have to think about what I'm going to be doing at 0 plus, because at that time, this resistor voltage could change suddenly. It doesn't have to be what it is at 0 minus. So it's actually no use to calculate this V naught of 0 minus here, because that may be completely different at 0 plus, in many cases at least. And so what I really need to do is to find this inductor current, because that's the one thing in the circuit, other than, of course, just source values, that cannot change instantaneously. And again, the reason for that is that V is equal to L di dt. And so if the current were to change suddenly through an inductor, that would give me an infinite voltage, which is not allowed. So therefore, I'm going to create a SOT current here, which is an essential step. I can have it point up, I can have it point down, doesn't really matter. But I'll just create a SOT variable, and it automatically names it here for me as IL, since it's going through the inductor. Okay, so having done that, then I want to change that inductor, which is still selected or red, into a short circuit. But remember, you have to, it won't let you do it after you've changed it, so you have to put the SOT current on before. It'll remind you of that if you try to do it prematurely. Okay, so we've changed that to a short circuit, and that basically completes the reconfiguration of the circuit. However, there actually is one more thing that I'd like to do. Since I don't really right now care about what this resistor voltage is at 0 minus, if I want to know it, I could find it out and just leave that there. But since I wasn't really asked to find that, I'm just going to get rid of that SOT variable. So I'm going to right click on that and just remove that SOT variable. Since I don't really need that at 0 minus, again, it's of no use in finding the same voltage at 0 plus, so I may as well just get rid of it. So I get rid of it, and I'm done reconfiguring the circuit. And now I can observe that this circuit is very clearly what we call hinged. Notice that there are two parts connected by a single wire here. Sometimes it's not quite that obvious, but here it's very obvious. It's been actually drawn that way. And as you may have learned in the last part of the introductory tutorial for DC superposition, when you have two parts of a circuit that are connected by a single wire, KCL tells us directly that no current can flow through that wire because I can draw a closed surface around either half of the circuit, and all the current that's leaving that surface, for example, has to add to 0. Well, there's only one current that could leave that, and that's through this wire. So therefore, that cannot have any current in it. And if it has no current, then it basically doesn't connect these two portions of the circuit in any meaningful way. And so this portion of the circuit really doesn't affect what's going on over here. And so to simplify this circuit, to make it easier to solve, I'm just going to get rid of that whole right-hand portion of the circuit. Now, if I'd left that sought voltage on there, then I would have to keep this, and then I would have to do a little bit more work. So that's one of the reasons I got rid of it. So I'm going to delete this, and delete that, and delete that just by hitting the delete key. And as it says, that was removably hinged with respect to the rest of the circuit. So now I'm left with something very simple. And boy, that's not going to be hard to find IL of 0 minus because, as you notice, there's no voltage source or current source to drive anything here. So therefore, that IL of 0 minus I already know has to be 0. And for that matter, this resistor is shorted. If I want to, I can even remove that resistor because it plays no role either. Being shorted, it has no voltage or current, so I could just delete that too. And then I'm left with what looks like a nothing circuit, but it's still something that has a solution, so that's fine. Circuit Tutor will allow you to do that. You don't have to do it, but you can. And I'm going to treat that as I guess a single loop circuit, although it doesn't really have a loop, but it'll allow you to treat it that way. And so I just select sought branch current, and all I need to do is to tell it that that current is 0. And again, I need to use that 0, not this term here, because I'm not allowed to put a 0 in there. That's really for non-zero currents. So I put that in, I'll check that, and that's correct, because obviously there's nothing driving current here. And that's all the equations I need. So now I have solved for the inductor current at t equals 0. In this case, it has to be just 0 amps. Okay, so now I need to analyze the circuit at the next instant of time, which is going to be at 0 plus. So I'll just click that button. And I can't do this, by the way, until I've done the 0 minus analysis. So if I tried to, it would give me an error and tell me that I basically don't know what I'm doing because I'm trying to do something impossible. So you want to make sure you do things in the proper order going forward in time and not backwards. Okay, so now it's relabeled the circuit for 0 plus, as you notice here. Everything's at 0 plus, and again it gives me the instructions to reconfigure and then go in the circuit editor perhaps and simplify and then write the equations. So I'll start by reconfiguring the circuit, and again I don't want to simplify in this mode, but instead I'm just going to basically change the switch. So the switch now, since I'm at 0 plus, that switch is no longer open, but now it's closed. So now I want to change this, instead of an open circuit, it becomes a short circuit. Okay, so much for the switch. Now the inductor, I'm at 0 plus. Well, you'd say, okay, is the inductor in steady state? Well, the problem is I just started a transient by closing that switch, didn't I? So what that means is I gave the circuit a kick, if you will, and it's not going to be in steady state at 0 plus. Now at t equals infinity, yes, it'll be in steady state, but right now it isn't in steady state at all. So it would not be correct at all, and indeed it'll give me an error if I try to change this into a short circuit. Instead, how do I treat this? Well, that's kind of a trick. And that's really why we found IL at 0 minus, which remember is turned out to be 0. What we know about an inductor is its current is not allowed to change instantaneously because V equals L di dt again, and if di dt if the current changed suddenly, di dt would be infinite, which would give you infinite voltage, which is not allowed. So therefore, this current has to have the same value at 0 plus as it did at 0 minus. Now, if that value didn't happen to be 0, then what I would do is actually change that to an independent current source. And I think it'll let me do that here, although I don't really need to do it. The problem is I don't think it'll allow me to actually put in 0 amperes here. So what I'm going to do instead is simply just change that to an open circuit. So I'm going to delete it. But normally, if it were some non-zero value, you would have to change that to a current source. You would want it pointing in the same direction as that sought current was. Now, if you forget what that was, you can always start over by restoring the circuit here. And then I just have to repeat what I did here, which was changing that to a short. And then again, So instead of changing that to a current source, I'm going to change it to a zero valued current source, which is just an open circuit. But that's kind of a special case here. That won't happen all the time because sometimes you need to have a current source of non-zero value. And the point is that you know the current through the inductor at that point. So therefore you can use something called the replacement theorem, which says if you know an element's current, you may as well replace that element by a current source that has the same value of current, because that's not going to change the rest of the circuit. So that's kind of the trick you use. Is normally you would replace this by an independent current source, not a voltage source, because again, the inductor, you don't know what its voltage is going to be, but you do know its current is going to be the same as it was at 0 minus. But as I said, in this special case, this is going to be 0, so I'm just going to basically delete that. And then I would also normally change the, well, no, I'm sorry, that's all that there is to do basically here. So I will stop reconfiguring. And now I just need to find this voltage. So to do that, it might help to simplify the circuit. I mean, I could just go ahead and do a mesh analysis or do a nodal analysis or something, but this circuit is just begging to be simplified, really. So I'm going to do that instead. And let's see. One thing I'm allowed to do here is source transformations. So I think, oh, if I make a source transformation, this will be single loop. Remember that single loop or single node pair circuits are the holy grail of circuit analysis. So I'm going to change this into a voltage source so that it knows what I'm trying to do. And let's see, that's going to be 2 ohms times 7 amps is going to be 14 volts. And I won't worry about the polarity just yet because I haven't really put it where I want it. So it needs to go up here. So I'm going to drag it up there. And then I'll check the polarity and say, okay, I wanted the plus sign down here basically, and that's connected to down there. So that's the correct polarity. And I now have the 2 ohm in series with the voltage source, and that's now a single loop circuit. So I'll check my source transformation, and that is correct. And that makes this a little easier to evaluate. And if I want to, I could also combine these 2 resistors in series. So the 2 and the 3 would make a 5 ohm, and then I'll change the other one to a short, so that I have a total of 5 ohms resistance replacing the 2 plus 3. And I'll check that combination. Now you might wonder, well, why didn't I also combine that with the 6 ohm? Well, remember that we want to know this voltage here. And if we basically had combined all 3 of those resistors or tried to do that, we would have lost this sought voltage. And in this particular mode of the circuit editor, it's not actually going to allow us to do a sought variable transformation, so we need to just do the source transformation instead. So now this is a single loop circuit. That's easy to analyze. So we're basically done simplifying. And now we won't have to do a full-fledged nodal or mesh analysis, which should always be avoided where possible. So I'm going to choose single loop here because this is a single loop circuit. It's not single node pair. And you may recognize that with a voltage source in series with 2 resistors, that is what we call a single loop or voltage divider circuit. So I'm just going to use the voltage divider formula to get my sought branch voltage. And so I say that my V naught of 0 plus is going to be equal to, I'm just going to use the standard voltage divider formula here. So I have my 14 volts. And then part of that 14 volts is going to drop across the 6 ohm. So I put the voltage, the resistor of interest rather there. And then I have to put the sum of the 2 resistors here, the 6 ohm plus the 5 ohm. So remember that 14 volts divided by that total of 11 ohms, that's going to be the current that's actually circulating in this circuit, and that current times this resistance by Ohm's law is going to be the voltage drop across this resistor. Now, one thing I always want to be careful about, of course, is the polarity, that dirty P word. So here you see that the plus side of the voltage source is actually connected around to the plus side of the sought voltage, and the negative side to the negative side. So that has the same polarity, so there is indeed a plus sign, but half the time there will be minus sign there, so we always want to be careful about that. So we'll check that equation. That is correct. And that's basically all I need. And now I just need to numerically evaluate that. So I'll just get my calculator out and take 6 divided by 11 times 14. And that will give us 7.636 volts. So I'll check that. And that is correct. And basically that will be summarized now. And now I just have to do the analysis under the other 2 conditions. Let's do the analysis at t equals to infinity first. So it's relabeled it now for t equals to infinity. And again, give me the instructions to reconfigure and then simplify and solve the circuit. So let's reconfigure first. And again, in the reconfiguration mode, we can't simplify, but we can change the switch. So the switch now is going to be closed because this is t equals infinity, of course, is much greater than 0. So that switch will be closed, and therefore it's going to be a short. And we also know that at infinity, the inductor will be in steady state. Therefore, that's going to be, according to V equals L di dt, that's going to have 0 voltage or be a short circuit. So we put in a short for that. And basically, we're done reconfiguring at t equal to infinity. So we just click done. Again, if you make any mistakes, you can always click restore circuit to go back to and start over again in the circuit editor. Okay, so now it would probably be good to simplify this circuit. I mean, it would be very foolish to start doing a mesh analysis or something like that here because there's a very obvious simplification, which namely this 2 ohm resistor is short-circuited because it's connected to the same node on both sides. So we'd like to get rid of that so we can use an easier analysis method. And so I'll simply remove that in the simplification mode here. I'll just remove that resistor. There we go. And the other thing to notice is that actually the current source is also shorted. And therefore all that current, rather than going through a path of some resistance here, it's just going to go through that short. And so the current really, that's essentially hinged or shorted from the rest of the circuit as well. So I can also get rid of that. And now it tells me I've deleted all the individually shorted elements. And that's interesting because now there's nothing left but resistors, which means, of course, that there's nothing to drive current in that circuit. Now, if I like, I can compress that up a little bit, but really, that's all I can do. Okay, so this is now either a single node pair or single loop. It really doesn't matter. I just have to really tell it that that voltage is going to be 0. So I can do, say, single node pair. Well, it doesn't. It's recommending, but it doesn't matter in this case. So I'm just going to say that voltage has to be 0, and that'll be fine. And that's all I need to do. So I've solved the problem at t equal to infinity. And now the last thing I need to do is to find the value of the R Thevenin, the Thevenin equivalent resistance, as seen from the terminals of the inductor for t greater than 0. So to do that, I click this button. And again, it gives me instructions, which always start with reconfiguring the circuit and then simplifying and analyzing. Okay, so let's reconfigure the circuit. And again, we're only interested in the time constant for t greater than 0 because for t less than 0, those transients already died out. We're not interested in that time constant. We're interested in the one that affects our actual solution, which is for t greater than 0. So first of all, we have to reconfigure the switch. So that's going to be now closed because it's t greater than 0. So we replace that by a short. Secondly, we're looking basically from the terminals of the inductor. So we're going to change the inductor into terminals where we can look at the rest of the circuit, if you will. Now, once again, we have to remember that if there were any dependent sources here, we would not be allowed to change that to terminals because you can't use resistive simplification in that case. You'd have to apply a test source, either a test voltage source or a test current source. But here, since there's no dependent sources, I don't need to worry about that, and I can just change them to terminals from which to view our Thevenin. And notice also that uniquely in this mode, we are allowed to kill sources just to save a little time here. So I'm going to go ahead and kill that independent current source because remember, you always have to do that when you're finding R Thevenin. You must kill all the independent sources, not dependent sources, but independent sources. And to kill a current source, I need to set it to 0 amps, which means an open circuit. So I will just delete that source basically. And the last thing here, I really don't want that sought voltage on there anymore because that's not relevant to finding this. So it's going to make me take that off. So I will just basically take that voltage polarity and set it to nothing. Okay, so that's the reconfiguration. Now we're ready to find that R Thevenin. So I'm done reconfiguring. Again, I can't simplify in that mode. And now if I wanted to, I could just directly enter the value. But let's just go into the circuit editor and do it step by step. So we see that we have two resistors here in series, the 6 ohm and the 3 ohm. So we'll replace that by a single 9 ohm, since 6 plus 3 of course is 9. And replace this by a short. And we check that. and that is indeed correct. And then finally, we have 9 ohm in parallel with 2 ohm. So the product over the sum there will be 18 divided by 11. And just checking in my calculator real quick, 18 divided by 11 is 1.636. So I'll change this to 1.636 and delete this other resistor so that I have a total of 1.636 ohms of resistance. And I can check that. That is correct. And now I simplified, of course, as much as I can, so I'm done with that. And now I just have to enter that resistance value. Again, that'll be 1.636. And that is the correct value. So basically now I have all the parameters I need, and so it's put me into the mode where I'm going to enter the final transient voltage expression for the voltage across that resistor. So I just need to select transient voltage in this case because my sought variable is a voltage rather than a current or power. And it'll give me the universal type of term I need for that. So remember now that at t equal to infinity, the exponential will have gone to 0 here, so this value won't matter, and we'll just be left with this constant. So that's going to be the value basically of the voltage across the resistor at infinity, and we've already determined that that would be 0 volts. So that tells me that this has to be 0 in this case. Secondly, at t equal to 0, I just get well, the exponential becomes 1, and so it's just this plus this is going to be V naught of 0 plus, which is 7.636. And since that's 0, that's easy to calculate. That just has to be 7.636 volts. And that'll add up to be the proper value at 0 plus. And finally, I need the time constant. And the time constant for an RL circuit is always L over R, which you can check dimensionally. And that means 9 henries divided by the Thevenin resistance, which is 1.636. So just do that real quick. And that is 5.5 seconds. And that should be that. And I just check the equation. That is correct. And basically, then I'm done. And if I like, I can get the complete view of the problem here. I'll just let that generate. Just takes a minute or two here for it to print all that on the screen. And it basically just shows you the general strategy here is outlined for solving this type of problem. And then it'll show you the details at each step in case you want to see if the computer did it a different way than you did it. That's might be useful to look at that, or if you're not sure about something that you did. And basically it just goes through and simplifies as much as we did at 0 minus, and then it does the 0 plus analysis, just like we did basically, using a voltage divider there. It didn't bother to combine all the resistors, which we wouldn't have had to do, but and then the 0 infinity, and just shows again that those elements are hinged or shorted. And then it just did the analysis for our Thevenin, and finally did the final transient expression, which is the same thing that we got. So that concludes the example at the medium level. Thank you.